This video is about finding rates from tables and graphs. So let's look at a situation about a pool. So a pool is being drained at the end of the summer. The following table shows some data from the situation. So we see that the hours are changing and the volume is going down in the pool. So what is the volume of the pool when it would start to be drained? So at 0 hours, the volume of the pool would be 1,200 gallons. How long did it take for the pool to drain? So for the pool to drain, that means there needs to be 0 water left in it. So 0 water, it took 8 hours. Number 3, how do we know that the pool is draining based on the table? So if we look at the table, we know that it's draining because our volume is going down. So the volume of the pool is decreasing over time. So now we want to look at the domain and range, and we got to figure out if decimals are okay. So in this case, we have our hours that are going from 0 to 8. Remember that at any time, the water is constantly draining. So these are just check-in points at the 2-hour mark. But we can still have water that is draining at a half hour, at 15 minutes. So our domain is going to be all real numbers, which we can write as an R with 2 lines that are between 0 and 8 because it took 8 hours for the pool to drain. The range then is going to be the numbers that go between this. So remember, just like every 2 hours, there's not going to be 300 gallons that magically disappear from the pool. It's draining the entire time. So our real numbers have to be between the highest and the lowest. So between 0 and 1,200. So again, we're going to make the R with 2 lines. It has to be less than or equal to 1,200 and greater than or equal to 0. Number 5, determine the rate of the pool by doing the jumps in the table. So if we look at the table and we look at our hours are always changing by 2's, and our volume is decreasing. So it's to be negative by 300 between each set of numbers. So our rate of change would be negative 300 over 2. So that reduces to 150. Then we have to use our units. So negative 300 goes along with the gallons, and the 2 goes with the hours. So we have gallons per hour. Is the rate constant? How can we tell? So we can tell because it's always changing by the same amount. So it has the same rate of change throughout the entire problem. So is the rate constant? Yes, because it has the same rate throughout the whole problem. Number 6, what does the rate mean in the context of the situation? So we kind of already talked about this. Our rate means that our pool is draining. The pool is draining at a rate of negative 150 gallons per hour. So the pool is losing 150 gallons of water each hour. In number 17, or in number 7, does the negative rate of change for the amount of water in the swimming pool make sense? Yes, because we're taking water out. So when we're draining something, we're removing it. So yes, because the water is being removed. What would have happened if the rate of change is positive? So if the rate of change was positive, that would mean we would be filling the pool. Number 9, draw a quick sketch with important parts of the pool situation. So if we have our axes, we're just going to draw 2 axes, one vertical, one horizontal. We would have hours and volume, and this would be the pool. Our line would start higher up on the volume, and it would go down to 0. So we should draw the line that's going down because we are taking water out, so we would have a negative slope. So now let's look at a different situation. A booster club is selling baseball caps. Find the rate of change from the table and verify that the rate is constant. So if we are looking at our table, the number of hats we're changing by 1, and then by 2 again, by 1, by 3. The amount of money collected is changing by 10, 20, 20, 10, and 30. So if I want to figure out if the rate is constant, I want to look at each row to make sure they reduce to the same thing. So we have 10 over 10, which reduces to 10 over 10, so we'll leave it. We have 20 over 2, which reduces to 10 over 1. 20 over 2, which reduces to 10 over 1. We have 10 over 1 again, and then the last one we have 30 over 3, which reduces to 10 over 1. So because they're all reducing to the same fraction, that means our rate is constant. So in number 10, describe a graph of the data. Is a line appropriate for this situation? So in this situation, what's happening here is they are selling caps and they are earning money. So in this case, we would have our data going up from left to right. So the graph would show the data points increasing from left to right. So if I was to draw a graph, we would have money, we would have hats, and then we would have dots going across. So we'd have 0, 0, and then we'd have them going up each time. Now, in this case, is a line appropriate? A line is not appropriate because we are selling hats, and we can't sell a partial hat. So a line is not appropriate because we can't sell partial hats. Number 11, let's look at another situation. So when you are pedaling on an exercise bike, the number of calories you burn depends on the number of minutes that you have been working out. Find the rate of change. So if we look at the time here, we're going from 0 to 15, which is a change of 15. 15 to 30 is a change of 15. 30 to 45 is a change of 15. And 45 to 60 is a change of 15. If we look at the calories burned, we have 0 to 105, which is 105. 105 to 110 also changes by 105, as does the rest of these numbers. So they all have the same numbers changing. So when I do rate, I want to do the dependent variable over the independent variable. So calories burned 105 divided by 15. And when we divide there, we would get 7. So we would have 7 calories per minute. So let's look at another situation. Shauna earns $10 a week for helping out at her grandmother's apartment complex. Fill in the table, then plot your points on the graph. So in 1 week, we know that she made $10, so 10 times 1 is $10 that she had saved. Then 10 times 2 would be $20. 10 times 3 is $30. 10 times 4 is $40. 10 times 5 is $50. 10 times 6 is $60. And for whatever weeks we have in the future, 10 times t, so our money saved, S would equal 10t. So what is the rate of change in this context? So in this context, we are looking at how much the money is changing every week. So if I look at just one row, I changed from 1 week to 2 weeks. That was a 1 week change. And from $10 to $20, that was a $10 change. So our rate of change then would be 10 over 1, which is equal to $10 per week. So that means that Shauna is earning $10 each week. What is the starting point? So the starting point here, think about if Shauna is not working at 0 weeks, she would have made $0 because she's getting paid $10 per week. So our starting point would be 0, 0, and it would mean Shauna earned $0. Shauna earned $0 at week 0. So we'll say Shauna at week 0 earned $0. Now, if Shauna was earning $15 a week, how would it change? So our original function rule from our table is that the money saved is equal to 10t. So if she was earning $15 per week, the coefficient in front of t would be changing. So then the new function rule would be the amount saved is 15 times t, which is the number of weeks. So let's fill out a table now if she is earning $15 a week. So at 0 weeks, she's earned $0. At 1 week, she has earned 15 because 1 times 15. At 2 weeks, 2 times 15 is 30. At 3 weeks, 3 times 15 is 45. At 4 weeks, 4 times 15 is $60. And at 5 weeks, 5 times 15 is $75. So we can graph both of our points. So let's go back and look at the 1 weeks and $10. So if we label our weeks counting 0 in the corner, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. To go up on the savings, we can go up by tens. So 10, 20, 30, 40, 50, 60, 70. So if we look at how we are changing, in the first situation, at 0 weeks, we made $0. 1 week, 10. 2 weeks, 2, 3, 4, 5, 6. For the second graph, we're starting at the same point of 0, 0, but we're going up $15. So this graph is going to be more steep than our other graph. So how do the graphs differ? The lines have a different steepness. Now let's look at a different situation. So Manuel made $1,050 working all summer. Use the table to describe what's happening. So as we are looking at the weeks going up, the money is going down. So he is spending money. So let's look at our rate of change. So we'll pick 2 points. So between 0 and 1, we changed by going up 1. And from 1,050 to 1,000, we went down by 50. So we have negative 50 over 1, which would be negative $50 per week. So in this situation, because it's negative, that means he doesn't have it in savings anymore, so he is spending it. So he is spending $50 per week. In number 15, what is the starting point? So at 0 weeks, he has $1,050, so it'd be 0, 1,050, and this means at 0 weeks, Manuel has $1,050 saved. So let's create a function rule. So our function rule, we could have the money saved S equals, he has $1,050, and then he is spending 50 per week. So we'll say 50 W, and we'll say that S is the savings and W is the weeks. So how much money will he have after 15 weeks? So we can plug 15 into W. So when we do that, we would have S equals 1,050 minus 50 times 15. We can just type that into our calculator all at once. So when we type that into the calculator, we would get $300. So that is how much money he has saved. When will he run out of money? So when he runs out of money, that means he will have 0 saved. So 0 equals 1,050 minus 50W. We can subtract 1,050 from both sides. So negative 1,050 equals negative 50W. When we divide by negative 50, we would get 21. So in 21 weeks, he would run out of money.